All right, so it's the appointed hour, and I wish you all a good afternoon or good evening, wherever you are. And welcome to today's webinar on the importance of proof testing. Now, I did do a proof testing coverage about 2 or 3 years ago, and it's interesting that this still comes up as being a question and people not fully understanding what we mean by proof testing or what the standard means by proof testing. So I decided we'll do another one, and that's the subject of today. I know that some of you have attended webinars before, but there might be some who haven't. So as usual, I shall just very quickly explain a little bit of the background regarding exida. Actually, this year is our official 20th anniversary. The company's been around now for 20 years. Originally, it started as with two guys looking at how to help manufacturers come to grips with the IEC 61508 safety standard that had been issued back in 2000. Since then, it's grown very rapidly, and now we not just do the support for manufacturers on the cybersecurity side, but we on the functional safety, but now we also do the cybersecurity as well. We also have full lifecycle support services for all three, alarm management, cybersecurity, and functional safety, which of course all three together are a very important part of the overall process safety and the safe running of the plant. And we have certification for personnel now on both the cybersecurity and functional safety. We also now do an alarm management program where you can become an alarm management practitioner right now, and the software tools to support all three life cycles. So exida has really grown. We've also become global, and you can see we have offices all around the world now, and we continue to add offices, and we will be continuing to expand and grow. How we measure success is what our market share is from the point of view of the certification. Plus also, we've moved away from being just owned primarily by two founders to being mostly employee owned. And that was a deliberate approach from the two founders because they want the company to continue and thrive after they've retired. So we continue to do that. We have now over 100 global experts, probably closer to 120 now. We've done over 1,000 certification projects, and with the Excellencia tool, we've modeled well over 500,000 SIFs now. So we feel that we're doing okay. As I mentioned to you earlier, cybersecurity is something that's fast growing now, and we're doing more certification for devices from the cybersecurity point of view. Reference materials, we've written books. There's lots of books that you can purchase through the website. We've also published a lot of free material, as I'm sure some of you are aware. These webinars, in fact, they're also recorded and they're available through the exida.com website. We have them recorded as YouTube videos, and you can find a whole host of topics under different categories for certification, for functional safety, for cybersecurity and alarm management. So I always encourage people to utilize the resources from our website. And there's also a lot of papers, white papers, that are available as well on different subjects. We do have the SAEL, which is the Safe Automation Equipment List, which you can access through the website, which will give you the list of manufacturers and devices that are certified and under different categories, such as sensors, logic solvers, final elements, etc. So again, that's another free resource that you can use. The SERH is our series of books that have basically safe safe equipment reliability handbook, which has all the failure rates that are built into the Excellencia tool. So you can, if you're not using Excellencia, you can get these books which have the failure rates. There's also a couple of new books coming out. I have one on functional safety for managers, which I'm hoping will be published at the end of at the end of March. It's going through review at the moment. And a little bit about me. I've been around in industry for more than 42 years now. And I began life as a design engineer, software hardware designer. I used to design some of the ICS Fire and Gas 2000 and the ESD 2000 range of devices and modules, and plus also an addressable alarm system as well, and an addressable fire system. But that was in the dim and distant past. These days, I'm working at exida. I teach primarily the FSC 100 course and also the Cybersecurity 101 and 102 courses, and I'm responsible for our end user business. Okay, with that brief introduction completed, let's get to the meat of what today is all about. And that, of course, is the importance of proof testing. So why is it important? Well, we're going to step through some of the reasons why as we go into the webinar. And really what we're talking about now is that from the IEC 61511 point of view, the safety life cycle as it's known, there's three phases. There's the analysis phase, there's the design and implementation phase, and there's the operation and maintenance phase. And some of you that have been on the FSC 100 course that I've taught will remember what I say about the old 20-20-20 rule. Typically 20 weeks in design, 20 months in implementation, and 20 years in operation. So the safety instrumented system with its individual safety instrumented functions is designed around a life cycle approach. This means that it's not just a once and done. In other words, we go through and do our risk assessments, we understand what hazards we have to protect against, we put in the mitigation through our safety instrumented system and our SIFs designed to meet certain requirements in terms of risk reduction to mitigate our risk, and then we're off and running. So that's just the first part. And when we think about 20-20-20, we're going to be spending more than 95% of the time of the SIS over the SIF's lifetime in the operation and maintenance phase. So what we have to make sure is that we continue to maintain the amount of risk reduction that we need. So that requires maintenance, of course, and it requires us to undertake the correct amount of mechanical integrity and making sure that components within the SIFs, safety instrumented functions, are replaced and refurbished when they need to be. We also need to manage change and make sure that any changes we implement do not detract from what we're trying to do in terms of achieving the overall risk reduction. And above all else, we have to make sure that we don't end up having potential failures on demand when the SIFs are called into action. Now, ideally, they should never be called into action because we should be doing everything correctly in the rest of the plant with the process, and that the basic process control system should be keeping things normally controlled. However, we know for certain that that's not always true. So if our SIS is our automatic layer of backup protection, then we have to make sure that we do as much as we can to minimize the prospect of getting a failure on demand. So just to refresh ourselves about the objectives of the safety life cycle, the whole point is to help us build safer systems, that we not have the same problems from the past, and we should also be matching our risk to our design. So it's a balancing act. We have to make sure that we have an optimum design to meet the required risk reduction that we need. And the other thing is to help us eliminate weaker link designs that actually cost a lot and don't really give us anything. But more importantly, it gives us a global framework. And the basic principle is that we want to manage the occurrence of systematic faults and reduce the potential for random faults. So these are the two things that we are looking to manage. If we look at the life cycle, as I mentioned to you, when you look at this, there's the analysis phase where we need to be making sure we've identified the potential hazards and the consequences associated with those hazards, which leads us into providing the mitigation we need to prevent those hazards from causing unwanted consequences within our tolerable risk. We then design for that. We test, we commission, install and commission, and then we validate, and then we start running. And you can see there's this one box here, which is clause 16, which governs operation and maintenance. And this is where we're going to be spending the majority of the lifetime of our SIS in this operation and maintenance side. So let's just talk about some fundamentals when it comes to safety instrumented systems and safety instrumented functions. We use probabilistic calculations to predict the likelihood of a failure on demand. We've all heard of the probability of failure on demand, and of course, with low demand mode SIFs, we talk about the average probability of failure on demand, the PFD average. And the purpose of this is to give us an indication of the likelihood of getting a failure that could cause us to fail on demand. And these probabilistic calculations are based upon a simple concept of constant failure rate during useful life. Now, there are other webinars I've done on this where I talked about the importance of understanding what useful life is. And we're going to touch on it here. So constant failure rate is determined based upon predictive or real data that's been gathered. Now we have, in the last 40 or 50 years, we have more than 200 billion unit operating hours of data that's been gathered. There have been various people gathering this, or various organizations gathering this data. And so we have pretty good, reliable data that we can use. So when it comes to looking at the flow of the information, the manufacturers themselves will put in information regarding failure rates, the types of failures. Are they safe? Are they dangerous? They list all of that. They also list specific instructions for installation, and if there are any anything that you need to do to meet a specific SIL requirement. When I teach the class, I euphemistically refer to it as RTFM, which is read the flaming manual. And it's surprising how many times when I talk to end users and ask them, okay, do you have safety manuals? They do not. Even some of the engineering companies who are engineering the safety instrument systems don't always have the safety manuals from the manufacturers. But that's an essential part of this, because we have to make sure that we configure the device right. If we're relying on diagnostics, is the device configured to run the diagnostics? And so on and so forth. Then we have to do a validation of our SIS, which is to make sure that the as designed, installed, commissioned SIS and its SIFs meet all the requirements. We also should be doing a cybersecurity audit now, because the standard was changed in 2016 to introduce cybersecurity requirements for SIS and BPCS. So we should make sure that we've done a proper cybersecurity risk assessment and we've implemented the relevant safeguards to prevent us having the potential for a cyber incident. Once we've done all of that, we've done our stage 3 functional safety assessment, which we need to do before we start up. And this typically could be done as part of your pre-startup safety review, the PSSR. Once you've done that, you get into operation and maintenance. And of course, we should have all our operation and maintenance plans and proof test procedures in place. The reason for all of this is to make sure that we don't introduce any potential systematic issues. I'm going to talk about that a little more in a minute. Then during operation and maintenance, we should be maintaining records. In other words, if we've had near misses, incidents, if we've had failures, what maintenance have we been doing, including all the proof test results. Are we making sure that we're doing that? And now the standard requires that we do a periodic, and it uses the word periodic, review, which is known as a stage 4 review. So an FSA 4 is to make sure that we are doing proof tests according to the requirements in the safety requirement specification. We're logging any potential near misses or incidents. We're recording all failures. We're analyzing failures, analyzing demands. We're making sure that our design is maintaining the level of protection we originally wanted. And then, of course, if we have to make any modifications or if we decommission, we're taking the SIS offline, then we have to look at that and we have to manage that. And that's part of the stage 5. So this is where we're focusing right now, operation and maintenance. So again, just to go back a little bit on what we said about probabilistic calculations are based upon a concept of constant failure during useful life. Most manufacturers know and recognize that components will follow what we call the bathtub curve. In other words, at the beginning, there's a high level of initial failures, which are known as infant mortality. Most manufacturers will try and screen those out during their manufacturing process by doing either burn-ins, as we call it. You might do some vibration testing, depending on the device, because they don't want these potential weak devices getting out into circulation and then failing and having to replace them during the warranty period. And then once you get through that, you can see what happens is it tends to flatten out until you get to a certain point where it then ramps up very rapidly. And that's known as the wear out. That's the back end, the wear out. But this bit in the middle, and what we do in safety is we approximate by taking this, an average basically across here. And you can see this is slightly pessimistic, but it gives us this ability to say, okay, we have constant failure during this period. It's predictable. Constant failure during this period. And this period is known as useful life. And again, in the safety manual, the manufacturer should indicate what the useful life of the device is. What that means is that you have to track this for each of the devices in the SIFs, and when the devices are coming up to the end of the useful life, they're either replaced or they're completely refurbished. This is very important because, as I've said, probabilistic analysis and probability calculations are based upon this premise. Once we get outside of here, it's no longer predictable. So in theory, you have no probability of failure because you can assume it's going to fail, and that's that. And that's why if you have a run to fail strategy, then as soon as you get outside of useful life, you no longer have any safety instrumented functions. So that means if we're taking this constant failure rate during useful life, we can say that our failure rate, indicated by lambda, is inversely related to the mean time, the average time to fail. So 1 over lambda will give us the average time to fail. So for example, if we have a pressure transmitter that has a total failure rate of 5 times 10 to the minus failures per hour, or what we call 500 fits. Failure per hour is basically 10 to the minus 9 is failure per hour. So 500 fits, 500 times 10 to the minus 9. If we invert that, we then get an MTTF of 2 million hours, which if we divide by 8,760 is the number of hours in a year, that tells us 228 years. Now, here again, this is not telling us that a transmitter is going to last 228 years. It's saying that this is a mean time to fail. So in other words, if we had a plant that had 228 of these devices, we could probably expect at least one failure per year. That's what that's saying. It's not the same as useful life, because the useful life of a transmitter may be, for example, 20 years. So this is the important thing to remember. And of course, when we come to look at the probability of failure on demand, there are different types of failures that we can have, of course. We can have failure modes, as they're called. So probability of failing on demand is a dangerous failure. So this is number one that we worry about. However, you can also have safe failures. In other words, a device fails, it could cause a trip, but that's a safe failure. Now, the trip, of course, is not something we want, because that means we now have to start back up again, and there's delays and there's costs. Plus, also, it's very risky when you start up, because most accidents will happen either during startup or during maintenance. So fail safe. And when we look at the reliability and the predictability of our SIFs and our SIS, we also want to look at what's our mean time to fail safe. What we call lambda S is the spurious trip rate, the safe failures. Then we might have diagnostics, and of course, if the diagnostics fail, then we need to know that the diagnostics failed, and this is called fail annunciation. And you can also have no effect faults, which is a failure that occurs that has nothing to do with safety. And I shall give you an example of that. So let's look at a typical transmitter, how a transmitter can fail. So depending upon how the transmitter is being used, if we are looking for detecting a high, the tripping, if our output ends up failing and saturating high, that's going to indicate a trip, and that's known as a safe failure. However, if we're looking for a low and we're now saturated high, that is a dangerous failure, because we won't be able to see the low. And the same with the drift. Usually if an output's frozen, we assume that's dangerous. We don't know where the actual reading is. If the diagnostic fails, that's annunciated. And in this case, there's an LCD. If the LCD fails, then this is a no effect failure. Okay. Somebody's asking questions. I'll deal with the questions at the end, if that's okay. We'll just keep moving, but keep your questions coming. So no effect failures are irritating, because you can't now read it in the field, but in terms of the transmitter working properly, it has no effect. So it's not going to affect safety. When it comes to final elements, now this is a different story. And if we're looking at de-energized to trip applications, one of the biggest things that we worry about in low demand applications with de-energized to trip is, when we trip, will the valve close? And the biggest issue that we have there is what's known as stiction. So for example, if our solenoid plunger is stuck, that is obviously a dangerous failure, because we cannot close. If the coil burns out, then the valve should close. That's a fail safe. If the actuator shaft fails, this is unpredictable, so we always assume worst case, so it's fail danger. If a seal fails, that's a fail safe. If the spring fails, that's a fail danger, because now we can't close the valve. If we've got pneumatics, if the air fails, that's a fail safe. If it binds, if the actuator binds, in other words, it's not able to move properly, that's a fail danger, because we assume worst case. And if the valve shaft fails, again, we assume worst case, that's fail danger. If the external seal fails, that's a no effect. If the valve internal seal is damaged, that's a fail danger, because the valve won't be able to properly close. And the valve ball stuck in position is a fail danger as well. So you can see that with final elements, there are a lot more potential dangerous modes of failure. And usually, when it comes to safety instrumented systems and safety instrumented functions, it's always the final element that is the major contribution, the major contributor to the PFD average. So just coming back to random and systematic again. Random failures, according to 1508 definitions, is a failure occurring at a random time which results from one or more possible degradation mechanisms in the hardware. Now, one of the misconceptions that a lot of people have is that random failures are all hardware related, systematic failures are human. But that's not necessarily the case, because humans can make random errors. In other words, somebody could be well trained, they could be following their procedure, and the procedure is correct, but there's something going on, they're not concentrating, they're having a bad day, haven't had enough coffee, and they miscalibrate the device. That is not necessarily a systematic failure. And so the other thing to remember is when we're looking at probability of failure on demand, we always consider random failures. That's why it's always important when you're recording failures in the field is to be careful about how you categorize them. And the rule that I usually explain to the class is to use the approach of saying everything's random until proven otherwise. That way you record the failure, won't throw it away. You can always go back and look and see if there's a potential systematic. An example of that could be that you have a transmitter from manufacturer A that's used widely in the system in different SIFs, and we have a failure of manufacturer A device. So we record that as random. And then 3 months later, we have a failure of the same manufacturer's device but in a different SIF. Now we would record that as random, but then again we'd look at, okay, why have we got two failures from the same manufacturer's device? And so there might be some potential systematic. And systematic is defined as a failure related in a deterministic way to a certain cause which only can be eliminated by a modification of the design or of the manufacturing process, operational procedures, documentation or other relevant factors. And in this case, I always refer to this as the 3 Ps. P number 1 is personnel. Are they properly trained and competent to do what they're doing? P number 2 is all about procedures. Do we have well-written procedures that are being followed? There's a lot of accidents have happened where procedures have not been followed. And thirdly, paper. Do we have a paper trail to show that we're doing what we said we would do? So this is what I refer to as the 3 Ps, and that's a good way to remember it. So random failures due to a non-deterministic system component, loss of functionality, which is typically hardware related, because humans can make random errors. And systematic is a cause, a bad requirement specification, design fault, wrong component, error in the software program, etc. And this is where the 3 Ps come in. So what is proof testing about? Well, 1511 under clause 16, and clause 16 governs all the O&M side of things, requires us to have a proof test procedure to be developed for every piece of equipment in a safety instrumented function. And this proof test procedure should describe the correct operation and correct diagnostic alarm and indications. And we need to do this regularly. The other thing that a proof test also needs to include should be a visual inspection. So when you come to do a proof test, you should always do an as-found review, which is look to see, are there any signs of corrosion? Do we have any loose terminals? Has anybody made some unauthorized modifications? And if we make a repair, we should also now complete a proof test. The standard now also requires that if there's an application program change, then you need to go back and test again all the SIFs impacted by this change. So it's not just a question of testing the application program. You need to go and rerun all the proof tests for the SIFs that are affected. And the only exceptions to this is if there's been an appropriate review and partial testing of changes that have been carried out. If you defer proof tests, you've got to have suitable management procedures in place. And now the standard also requires you to define a maximum repair time. So when you're putting if you're doing it online, if you're putting a SIF in bypass to test it and then to either restore it or repair it, you have to specify your maximum time to do that. So you can't just leave the SIF in bypass. And there was a case where a plant manager did an audit and was horrified to find that one of the SIFs had been left in bypass for 18 months. Nobody realized it. Proof test intervals have to be specified in the SRS. That's a requirement. So the safety requirement specification will say, for example, that the proof test interval is 18 months. Now, if we've done our SIL verification, our PFD calculation, based upon an 18-month proof test interval, once we get more than 10% outside of that, then we start having an impact on the risk reduction factor. So, for example, if we said 18 months and we miss it by 2 weeks, okay, that's not a big deal, but we should really record the fact that we're not able to do it on time and see if we can improve it or not. Now, 2 weeks is not a big deal. If we miss it by 3 months, now that is a big deal. And what will happen is it will affect your risk reduction. And if you have a target risk reduction that's defined in the SRS, then you'll find that you will not be meeting that. So it's important to make sure that the proof tests are conducted within the SRS requirements and no more than 10% outside of it. And again, we should be recording that when we do our FSA4, our periodic review. We should look at that and see how we can improve that. Again, the mean time to restore is how long does it take from detecting if we've got a problem from a proof test to repairing the problem or restoring the SIF to normal operation. So typically in the SRS, it may say that everything is 24 hours except final elements, which is 72 hours. That's a typical. And the purpose of a proof test now is it should be designed to find potentially dangerous faults that the diagnostics can't find. So here again, we go back to the safety manual, because the manufacturer's safety manual will have a recommended proof test to achieve a certain coverage factor. In other words, how effective is it at finding potentially dangerous faults? Because it's the dangerous faults that are going to cause us to have the failure on demand. And of course, our personnel need to be regularly trained and assessed to make sure that they're able to follow the proof test procedures, that they're able to implement any changes correctly. So this statement here, the purpose of the proof test is to verify that safety instrument function works properly. This is wrong. The purpose of the proof test is to detect any failures not detected by automatic online diagnostics. We're looking in particular for potential dangerous failures, diagnostic failures, parametric failures, as well as potential unauthorized program changes. So this is the purpose of doing the proof test. So the strategic proof test here, as I've said, is to try and find potentially dangerous faults that the diagnostics have not been able to find. So we can actually design our proof test procedures so that they're easier to perform, cost less, and are more likely to actually get done. So you can design the best proof test in the world, but if it's going to take 7 hours, guess what? It's not going to get done. So I always tell designers that you don't want to design in isolation. You need to talk to the O&M people, find out, number one, their sore thumbs, and find out what they can actually do. I mean, we had one client that came to us because in order for the engineering company to meet the target SIL for the SIFs, they had come up with a 3-month proof test interval. And of course, the end user was saying that's impossible for me to achieve. There's no way we can do 3 monthly. So they were automatically set up to fail. So it's very important that you understand the capabilities, if you're a designer, of the end user. By understanding these failures, these dangerous undetected and enunciated undetected failures in our instrumentation will help us to improve our coverage, test coverage, as well as lower our cost. And then we can detect program changes via the tools that are built into most products. Most of the logic solver manufacturers have revision control, and as soon as you download it, it can track that particular revision, and therefore you can do comparisons to see, okay, is what I have in my database that I know was last updated the same as what's in my logic solver? So that's the reason why it's very important to have the safety manual. If you're using Excellencia, Excellencia automatically has all of the information in there, and you can generate proof tests based upon the equipment you've chosen, and it will be based upon the manufacturer's recommended proof testing. So the safety manual, again, is something that you need to have because it contains important restrictions on how the product has got to be used to maintain safety. So there'll be environmental restrictions, design restrictions, and of course our periodic inspection and test requirements, as well as the failure rate data. So when we look and just taking a very simple, simplified formula, simplified approach to looking at PFD average, PFD average is approximately lambda D, which is the dangerous failure rates, because that's what we're interested in, multiplied by our proof test interval divided by 2. And this is simple because it's assuming perfect proof testing, which means we can find and fix all the dangerous faults, which in reality we cannot. There's no such thing as 100% proof test coverage. Some of the logic solver manufacturers can claim 99% or better because of the diagnostics, but when it comes to final elements, that's never going to happen. So if you are using 100% now, then think again, because you're just fooling yourself. So for example, let's look at a butterfly valve and a pneumatic single action actuator, which we will use to implement close on trip function. So if we did a full stroke test of the actuator valve assembly, does that find all the potential dangerous faults? Or are there any left? Well, of course, we won't find all the dangerous faults. You know, a full stroke test is fine, means you can move the valve all the way across, but you don't know if you've got damaged seals, you don't know if you've got a damaged butterfly, and you could have a damaged shaft. So even though you've done a full stroke, it still might not fully close. So now we have to include this concept of imperfect proof testing and just taking our simplified formula for a PFD average in a 1-out-of-1 configuration, in other words, single device, so we have single sensor, logic solver, final element. We now have to include this imperfect proof testing, and we talk about CPT, which is the effective coverage of proof tests. So in other words, this is 0 to 100%. So if it's perfect, it's 100% or 1. And then because of imperfect proof testing, we now have to consider the operational lifetime of the SIF, which is known as mission time. Because if you look at the formula now, if it's 100%, then this has no bearing, because this goes to 0. If it's not 100%, now every time we do a proof test, it means there's always going to be a percentage of dangerous faults we can't find. So instead of coming back all the way down to 0 with our PF, our probability of failure, there's some element left. And so every time we do a proof test now, it's not going to come back to the same point. And you can see, let's say if we are 80% effective with our proof test, then every time we do a proof test, we are only going to get 80%. So there's 20% each time that we can't, and this accumulates over the mission time. And what happens is our PFD gradually rises. And it can get to the point where the PFD average now has moved from one cell down to the next. So this is why we have to make sure that we do our proof testing effectively, and we are watching the useful life. So the correlation between proof test interval and mission time and proof test coverage is very important. So if you, for example, if you set your mission time at 30 years and you want a 4-year proof test interval and you're trying to get to SIL 2, think again. You will not be able to do that. You can do partial valve stroking, which will help, but typically you have to understand this correlation between mission time, proof test interval, and the required SIL. So this is very important to understand, and this is why it's so important to make sure that we are doing our proof tests in a timely fashion. We're not going outside of the 10% margin, and we're following the proof test procedures to ensure that we're able to get the best coverage we can get, remembering that there's no such thing as 100% proof test coverage. Okay, so in summary, the integrity of our SIF is maintained as a result of doing regular proof testing. We still have to be mindful of the useful life, remember, because proof testing helps us maintain it. But once we get outside of useful life, we have no longer a probability of failure on demand, because we cannot rely on it being constant failure rate. So we effectively have no PFD calculation. The proof testing has to be as effective as it can be, and if we are doing it properly, then we can maintain the integrity of our low demand SIFs. There is no such thing as perfect proof test, and that's why it's important to understand what the manufacturer is recommending when it comes to proof test and proof test frequency to maintain the integrity during the useful life of the product. And if end users, if they don't have the safety manuals, then you have to make sure that you are following the correct refurbishment and replacement of the devices when they come to the end of their useful life. And this is difficult because I know if the device hasn't failed and you go back to your managers and say, well, we need to replace these devices, and he says, well, have they failed? And you say no, then he says, why? There needs to be an explanation as to why. And this comes down to culture again. And one of the problems I've seen quite often is that managers don't fully understand reasons why we do some of the things that we do from a functional safety point of view. Again, failing to perform the proof test or extending the period between the proof tests beyond the 10% will impact the integrity of the SIF. That's a very important thing to remember. Incomplete maintenance is another problem. If we fail to do our maintenance, if we fail to follow the mechanical integrity, that will also have an impact on the integrity of the SIFs, and they will degrade much faster. Proof testing helps maintain this integrity during useful life and over the mission time. It is no substitute for obviously tracking the useful life and making sure that we do replace or refurbish. So setting the mission time is important, and a lot of times people will set it based upon their final elements. So if the valves have a 10-year useful life, then they may say, well, the mission time is 10 years. We've had some clients that say mission time is 5 years. It's just a question of it comes down to the site practices and how things are done from the end user perspective. But either way, we have to make sure that our useful life is tracked. We have to make sure the devices are properly maintained, and we make sure that we do our proof testing effectively for our safety instrumented functions. And of course, mechanical integrity should account for useful life and when we have to replace or refurbish. So these are the things to remember. And that's why proof testing is such an important part of being able to maintain the integrity of the SIF. And now one of the reasons why the standard requires an FSA 4 is because end users were not tracking the performance, because the IEC 61511 standard is a performance-based standard. So in order to be able to measure your performance, you have to have indicators, or you have to have metrics. And proof test frequency and proof test effectiveness are metrics that you can monitor to see how we're sticking to the proof test intervals. Are the proof tests actually finding problems? And are we getting failures? And what you'll find is, if you don't do the proof testing properly, you'll probably end up with more failures and more potential spurious trips than you want. So it makes sense to do the proof testing for a number of reasons. Okay, just a little bit about courses coming up. In the UK, we have the FSC 100 coming up in Warwick next month. I'm actually teaching that one. We have a fire and gas coming up in Aberdeen. We have an Excellentia course in April in Warwick, and we have a burner management course in May in Warwick, as well as another fire and gas detection in Aberdeen in September, and another FSC 100 in October. So if you're interested, we do, in the FSC 100, we go into a lot more detail on the SIS and the SIF design and verification, and also the testing. If you're specifically interested in the O&M, there is an O&M class that we have, and if you're interested in that, you can ask Ali Coles for information. Elsewhere in Europe, we're running courses in Italy, in Norway, Denmark, Germany. Again, if any of these are of interest to you, you can find the full schedule at exida.com/training. You can contact Ali Coles in our UK office. She'll be happy to help you. And of course, if you want to know more, follow us on Twitter, Facebook, LinkedIn. And if you've got a suggestion for a webinar topic, by all means, send it to academy@exida.com. We're always happy to hear from you. And now let's look at the questions. So I could see we were getting a few popping up as we went through. Okay, one thing that I think is challenging related to proof testing is, how do we test equipments that don't have safety manuals, especially actuators and valves? This happens especially for old equipment. How do you handle this type of situation? Well, here again, typically if the equipment has been there for a while, there should already be test procedures in place to be able to do that. If not, then we actually offer a service to help with creating proof tests to do that. And so we'd be happy to help you with that. The term safe failure is misleading. It could close a valve, which causes, I've lost the rest of that comment. Let's see what it says. Which causes a high severity event. Well, again, when we talk about safe failures, we're talking about failing safe. So that means understanding. And when I teach the class, I say, when it comes to the safe failure situation, it may be a de-energized to trip, it may be an energized to trip, or it may be a stay put, depending upon the process. Because if it would cause a potential hazard, if we suddenly shut down, then we don't want to do that. So this again comes back to understanding the application, and the designers should be aware of this. And they need to make sure that if shutting down causes a potential hazard, then you don't want to do that. So you may stay put and you'll generate an alarm, and the operator has to do something. So I agree, safe failure has to be properly defined, and that's one of the things I cover on the FSC 100 course, is what do we mean by fail safe? Testing the actuation of a SIF is considered part of a proof test. Usually we call this kind of test as a functional test. Well, again, functional testing is to make sure the thing works. What the proof test does is to try and find potentially dangerous faults. So it's subtly different. And that's why I say the safety manual is important to follow, to see what the manufacturer recommends for a proof test. Is the no more than 10% out backed up by research? Well, you can do it yourself. If you using an 18-month proof test interval, if you've got Excellencia, it's very easy to do this. You can go in, you can do a calculation with a risk reduction factor for a SIF with 18 months, and then you can move the SIF out by more than 10%. And you can see immediately what that does to the risk reduction factor. And depending on where you are, if you're a low-end SIL 2, for example, where we've got a risk reduction factor of 110 or 115, and you move out by more than 10%, you'll probably find that you move down into a SIL 1. So you can either do it by using Excellencia, or you can do it the hard way by using Excel or some other tool to do it. But it's not necessarily research. You can prove it to yourself very easily. An idea, what do you think about doing a simulation of a proof test in a future webinar? Yeah, we could certainly think about doing that. Give that some thought. Thank you for that idea. If we replace a transmitter, we need to proof test a specific loop. What about a change in software? Yes. Well, as I said to you, application software program 1511 now requires you to test all the affected SIFs. So you need to know which SIFs are going to be affected by the application change, and then you need to rerun the proof tests for those specific SIFs. If the proof test is for an individual component which make up the loop, what do you call the end-to-end test, which I assume the testing interval is based on? Again, a proof test has to include the sensor, everything in between, the logic solver, any output interface devices, and the final element itself. So when you talk about a loop, you have to be careful what you mean by that. When we talk about a proof test for a SIF, we're talking about all the instrumentation that is included in that SIF. Now, in some cases, because the logic solver is being used to handle different SIFs, you may not want to test the logic solver every single time. And some clients structure their proof tests around equipment, types of equipment. So it's a question of how you approach it, but you have to make sure you include everything. And that's what the test interval is based upon. So when you look, and again, if you're using the Excellencia tool, you can define the proof test interval for the sensor, you can define the proof test interval for the logic solver. When we talk about sensor, we're talking about sensor subsystems, so that's all the interface devices as well. And the same with the final elements. You can define a proof test interval for that, and also if you want to do partial valve stroking, you can define that too. Could the recording of this presentation be emailed? Well, no, it's available through the website. When is it a functional test, and when does it become, albeit imperfect, a proof test? Well, like I said, functional testing is normally done when you're doing the verification. A proof test is run specifically to try and find dangerous faults, and it's different from a functional test. That's why I say if you're not using Excellencia, then you want to make sure you have the safety manual so you understand what that proof test is and what coverage it's giving you. Now, in some cases, and I've come across this, end users who are very familiar with certain types of equipment, and we have a customer that has done this, has developed their own proof test based upon their knowledge and the performance of the instruments with them. And that's fine. And they get a certain yield out of that proof test in terms of the coverage factor. So you can start with the manufacturer's recommended proof test. That's a good place to start. And then as you become more familiar with the equipment and the performance of the equipment, then you can adjust it. I mean, this is the whole point with the standard. It is a performance-based standard. So as long as you're measuring things correctly and you can show that you're either exceeding performance, in other words, you're having far less problems than you originally envisaged, then you can start looking at, well, maybe we can stretch out the proof testing interval a bit. So that's the point of the standard, is to help you. It doesn't tell you how to do things. It just tells you this is what you need to do. How you do it is up to you, but as long as you measure performance and as long as you can prove that your performance is being maintained, or if it's better, then you can use that to justify making changes. So I always say this when I teach the class, it is a balancing. It's always a balance, and that's the idea of the life cycles, to help you balance. Balance in terms of the cost, in terms of maintaining the integrity, in terms of safety, all of these things. Okay. Well, we're almost up to the hour. I appreciate all the questions. Thank you for that. Thank you for your attendance. And again, if you have other questions, my email's there. I'm always willing to answer any questions that people have after the webinars. And if there's specific topics, I like the one about the proof test. I'll certainly give that some thought. Please let us know. Well, thanks very much for your attendance, and enjoy the rest of your day.